I can be any kid on the block. Oh, yeah? Yeah!
My name is Kai Driscoll with Team SSADAB, and this is our final project of the Rock'em Sock'em Robots. Before we get started, here's an introduction to all the teammates who worked on the project. Madeline Polly was in charge of code for the project. I was in charge of making the mechanical aspect of the base design where the robots are positioned and also helped with the code. Alexis Pack was in charge of the mechanical condition of the robots themselves, and then lastly, Jade Valdez was in charge of the breadboarding of the project. All of us here are aspiring electrical engineers.
The main goal of our project was to make a Rock'em Sock'em clone using a mixture of electronic and mechanical features. While the original game uses a mechanical mechanism to make the robots function, ours would be operated with buttons and servo motors. It would also keep track of the score and winner digitally through a display in the clue board. In our project, we use a variety of skills such as 3D printing, laser cutting, and coding. Some of the challenges we faced were incorporating these things together when we worked on them separately, and had limited time to work together. An idea that may have worked originally might need modifications when putting it together with everyone's separate pieces.
The servos receive data from the clue board. Every 2 servos are powered by a 9-volt battery, and the clue is powered by a 3.7-volt battery. The 6 buttons are powered by the clue, and they send data to the clue when they are pressed. The main functions of the code are to trigger the respective robot arm when any of the control buttons are pressed, and simultaneously keep track of the score on the clue. In order to do so, we attach a sensitive button to each robot's chest, and when either of those buttons is triggered, the respective score increases by 1 point. Then, when either score reaches 10 points, the code stops running, the scoreboard display is replaced by either red or blue wins, and after 2 seconds everything resets so that the game is ready to be played again. The biggest struggle with this code was having functions run simultaneously, such that multiple robot arms could be triggered at the same time while a scoreboard was still running. And in order to accomplish this, I used a library recommended by Professor Blum called Gamepad, which utilizes interrupts.
First, we made a prototype for the enclosure with cardboard by making a rough estimate of the dimensions. After laser cutting the box, we decided that measuring in centimeters would cause too much confusion when working with programs, so we switched to inches. Of course, cardboard would not support the robot, so after adjusting the length to be in inches, we purchased wood and cut that to the adjusted model to account for screws and controllers for the players. The hardboard wood we got was high-density wood and very hard to cut with the laser cutter. After 8 or 9 cuts, we finally had a box strong enough to support the robots. We also created a shelf to hold controllers for the players, but we had to glue it to the box and its supports because screws would obstruct the surface where the buttons needed to be.
The very first thing I did before I started designing the robots was go out and buy a real Rock'em Sock'em toy. I did this to get a good idea and reference on how the arms are working and the size of the robots themselves. I started taking apart the robots and investigated the mechanics that went into them. I first did some quick sketches and measured out how big the servos were so I can make the chest piece big enough for it to fit. I knew with this design I wanted the chest pieces to be separated in the middle and the legs to be together by themselves. I went into Onshape and started creating each piece. Altogether, there are a total of 10 separate pieces that went into making just one robot. The arms were by far the hardest part to make. Trying to figure out how the arms were going to work was a struggle, so I reached out to others who were more than happy to help me out. Once I got a design I thought was pretty reasonable, I printed them out and tested them to see what changes needed to be done. After weeks of doing this process, I was finally able to get a design that will satisfy the project. Since prints do take a long time, I was only able to print one robot and not the other.
I first made note of what the specific goals were for the project and what parts we needed to accomplish that. On a design that required 4 servos and 6 different buttons, we had a lot of power draw. In order to not break the clue, I powered the servos from a separate source, 2 9-volt batteries and a battery clip connector. Each battery would power 2 servos, which meant each separate robot would have its own power source, while the buttons all drew from the clue itself. In order to still have them a part of the circuit, all ground from the servos connected back to the clue, and the data wires for their respective slots on the dragon tail.
Overall, everybody was able to finish their part of the project, but since we were not able to see each other very often, the final product was not finished. Altogether, however, we learned and battled through obstacles to get where we needed to be. The virus might have restricted us in many ways, but we got through it, persevered, and had fun with it.